What's up guys, Francesco here. Today we're going to find out how to use an implementation of a swarm intelligence algorithm called DFO, Dispersive Fly Optimization, to solve a simple logic game, a card game basically. So yes, let's check it out. Let's get cracking. We've got the problem. It's a card game, as I said, that we're trying to solve. And in this card game, we've got 10 cards. We start with 10 cards, and we want to find out how to arrange them into two groups so that the sum of the first group is 36 and the product of the second group is 360. Now, apologies if my computer is really loud. The vent of my laptop is really loud, but that's what it is. So let's quickly display how this works. So let's say that the cards in red are now in group 2 and the cards in black are in group 1. How many possibilities if we were just checking at random? Well, each card has 2 possibilities. So if we multiply the possibilities of the first card and the possibilities of the second card and so forth, we get 2 to the power of 10. That is 2 times 2 times 2 times, and that's 1024. Now that's as many possibilities you've got by just randomly choosing some cards to go into group 1, some cards to go into group 2. Okay, well, how are we going to solve this? As I said, we're going to use a swarm intelligence, artificial intelligence basically, algorithm that learns from its attempts at tackling the problem and finds hopefully a path which is much faster than just checking at random. In particular, this program is explained in its workings in a website, on my website, in a blog that I've written about it. There we go. DFO, Dispersive Flies Optimization. That's the name of the algorithm. You've got all the references to who invented the algorithm and why it works, how does it work, and so forth. I'm not gonna that face was quite funny. We're not gonna really go into the details of it because it would take a video just to do that, and we assume that we get the basics of it. The basics of it is we have a bunch of simple agents that my implementation handles automatically, so you don't have to worry about it. Each agent carries a solution. So let's say that agent 1, this one here, carries this solution 1, 4, 6, 7 into group 1, into group, let's call it group 0 and 1. And instead of 1 and 2. So these are the cards that go into group 0, so obviously 2, 3, 5, and 8, 9, 10 into group 1. So the first group and the second group. This is the solution. Now, let's say a second agent is going to carry a different solution. So cards number, let's say that this solution is actually very silly and very similar, not silly, sorry, very similar to the other one, and the difference is that card number 7 has gone from this one to this other group, and so forth. Let's say we've got 10 agents like this. They start with these random combinations, and maybe one of them is correct, or maybe not. Most likely it's not going to be correct. They will need a way to find how wrong the solution is, so that they can say to one another, my solution is not that far from where it should be. So maybe you guys should change your solution for something which is closer to mine. Now the algorithm is called dispersive flies optimization because this behavior of hovering and and collecting around a target, around something that catches the attention of the individuals, is a behavior seen in flies as they see a source of food and they tends to go towards it, and as one guy tends to go towards it, everyone else tends to follow, and it creates a kind of a chain effect. So that instead of trying out all the possibilities, we just try a few, and then we start to move these the attempts that we make afterwards, not at random anymore, but based on the solutions that we have and how close they are to the real solution. If that's a bit too much, well, all I can say is have a read at this, try to understand how this works, because now we're not going to go through the details of the algorithm itself, we're just going to implement it. Now to implement it, we can we're not going to implement the algorithm itself, we're going to implement the solution. The algorithm has already been implemented, I've done the hard work for you, so all you have to do is to go to my GitHub, github.com/fpert041/DFO, and then you clone, copy this, come back here, open a terminal window. I'm in desktop right now, so my terminal is pointing to this. Oh no, that's not what I need. I need to do git clone and then paste this. I'm gonna execute it, and I'll pause the video and then restart when the download is finished. Doesn't take long, but still, no need for you to wait around. Oh, here we are back, and we now have this folder called DFO right here in the middle of the desktop. It's the same, let's close this, it's the very same code that you find here. Open Xcode or your IDE in your operating system. I'm on a Mac, so Xcode is what I've got, and create an empty C++ project. I'm going to create a repo. Now this is nothing. What this does is just nothing. It's gonna print to console hello world, right? Is that what you do? No, it doesn't even do that. Oh yes, it did. Look, hello world, done. That's the dumbest program ever. What we need to do is we need to link this, which is it's the algorithm folder, and it comes in the package. How do we link it? Well, we just do this. Look, create groups, our targets to done. Now, if you're not on a Mac, what that did is that it took the source files in there and added them to the IDE, to the project, so that now the project can find the source code. We also need to link the actual DFO, right? So what you have to do is you have to say, okay, where is this? Well, we've created the program, okay, in examples, CPP, there we go, okay. In particular, main is here. So main needs to go up 1 level, up 2 levels, up 3 levels, up 4 levels, and then into this main folder it has to go into DFO and then find this, okay. So up 4 levels, DFO HPP. Just to test, let's see if it can find it. It would throw an error if it couldn't. It did find it. Brilliant. Now, create an instance of the DFO and set it up. So what do we need to set it up? Well, we need for sure to set the dimensions where our flies, our agents can sort of, no, better to say, we need to set the dimensions of the search space, which is the space across which the flies, our agents can go through. In this particular, you can visualize this as sort of the space in which you're doing the search. In this particular case, let's bring back our thing. Okay, let's make sure that I move. All right, cool. So in this particular case, you know what? Let's delete this. Our search space is all the possible combinations of these cards, and the dimensions are the dimensions of this space. Now, if you only had 2 cards, say you only had 2 cards, that's what you had, okay, the space would be the positions this card could take. So it would be a 2-dimensional space because an agent would contain these 2 elements, these 2 features, these 2 coordinates, if you want. If you imagine them as a fly carries a solution, and a solution is made of 2 things. So this is a 2-dimensional space. Of course, you've got 10. So what space is that? It's a 10-dimensional space. DFO dot set dimension setdim 10. What else do we need? We need to specify how many flies we want. Now, the algorithm has a default of 20. Let's just leave it by default. That's not fundamental for us to change the number. Plus, I know a good number, but let's say that, let's just imagine I haven't done this before, so I don't know the number. Well, let's start with the default 20. What else do we need? Well, we need to specify the initialization width, that is each dimension. Okay, what can it, each dimension? Okay, because dimension is a word that I guess it can create confusion. What is that? Why is that dimension? Well, because if you have read my blog, then you would know what the dimension is, but if you haven't, just very quickly, a dimension is one dimension, okay, is one feature, okay, that the flies carry with it. So in the real world, flies have 3 dimensions to locate their position because they're animals, they exist in 3D space. In any example that you can think of when you use this algorithm, you have to basically picture your problem as a problem that has solutions that should be represented as a vector of features. In this particular case, it's a vector of 10 cards, and each card can have a position, 0, 1, or 1. 0 or 1. If it's 0, it's group 1. If it's 1, it's group 2. Okay, these are the possibilities that each feature of the solution carried, or a hypothesis, or there is an attempt to a solution that each flies carries with it can be either 0 or 1, because it can be to group 0, group 1, or group 1 or 2. You know, we've got 2 groups, and I call them 0 and 1. So each fly will have 10 dimensions, will have 10 features, will have, in practice, what the algorithm will make it is basically a fly has 10 features, it has an array of 10 numbers. Okay, that are really what it boils down to. It's an array of 10 numbers. So by doing this, I make sure that my flies have that, and I want to say each of these dimensions, okay, set search space width can go from 0 to 1. Okay, because obviously you've got numbers that can be, you've got cards that can either go to group 1 or group 2. So I want to initialize them with a number that can be from 0 to 1. By doing this, you initialize, you specify that the initialization of each fly, when I create them, can go from 0 to 1. Okay. Now, when I run the program the first time, now dfo dot, let me think, what do we need next? Next, we need to specify what algorithm we want to use, whether we want to use the algorithm that only checks the neighboring flies, so each fly is only aware of what's happening to the solutions of the neighbors around it, or so that it can keep the best, it can keep track of the best in this world, that is the solution overall that is getting closer to the real solution. Now, the algorithm would work with either, but I find that with problems where you have solutions that are pretty good but not that good, and you have many of them and they tend to be surrounded by a large space of solutions which are much worse than them, then the algorithm can get stuck. Getting stuck means that a solution that it thinks is the very best it can ever get to is not the real solution. It simply means that all the agents for some reason have gone close to that space, close to that solution, and they were like, oh well, that seems to be the very best that we can find. They get there closer and closer, and even though the algorithm has a mechanism to send random agents away from the solution that they think it's the best, just in case it's not the best, the algorithm tends to get stuck. Now, the positive advantage of keeping track of the best in this swarm is that it's more stable. Once it finds a good solution, it tends to stay there and not to lose it. Whereas if it only looks at the neighbors, sometimes the swarm disintegrate, and you can see all this stuff with an example that my repo comes with that visualizes it. But for that, you need open frameworks, and it's a different thing. So you'll have all the explanations in the README if you want to implement that, if you want to create that. But this is a different tutorial. I just want to take my DFO and quickly set it up so that it works on a simple problem, and perhaps you can start to see how this works. In this particular case, I want to, in fact, I'll just leave it. This is fine. We've got 10 dimensions with our 10 cards, or 10 parts of the solution, of a possible solution. And we've got the search space width, which is 0 and 1. Now we need to define a fitness function. This is the most important thing. Okay, this is what characterizes your problem. In this particular case, we're going to pass in a lambda function that has to take in, in fact, hold on a second. Come on, yay. Now it has to take in a function, okay, that takes in a vector. So I'm going to use a lambda here, that is the temporary function, and here is what we do. We use this symbol that says, hey, a lambda function is coming. We says this lambda function takes in a vector of doubles, and this is, by the way, is required. It's just you need this in any fitness function that you define. And if you want to know why, you can dig into the DFO implementation and the actual algorithm, but for this tutorial it suffices to know that it works. We've got a lambda function, and this function returns a value. It has to return a w, a double fitness. Now at the moment fitness is equals to 0, and we return it. Now we have our fitness function. Our fitness function is this: set a number to 0, return that number. Now, obviously, as you can see, this is not really working, because it wouldn't work, because this is doing nothing. Now, I can explain what this is. It's the moment that you find out what this is. This is a random. It's not random. No, it's a vector of doubles. It's a vector of numbers, and these numbers are our features, our parts of the solution that each fly carries around. Or if you want to think of the fly as an actual fly, you can think of the dimensions of the world where the flies exist. Because the hypothesis, the attempted solution that each fly is, in our basically conceived as the coordinates that define the position of that fly. This is how the algorithm works. This is how we define our flies, and how then behind the scene the algorithm optimizes by basically moving flies close to the ones that have the best solution. And the best solution is the one that has the lowest fitness, and the fitness is what we calculate within this function, which is basically what our problem asks us to do to solve it. So let's think back at our problem. We have our cards. By the way, it's fair for you to see me. There we go. So you know I'm not cheating. I'm just here live coding for you. You've got these numbers. So we've got a vector number, and each number can be either 0 or 1, depending whether it's in either box. Now, this is not actually true, because when our flies initialize, they're given a number which is randomly between 0 and 1, and as the program progresses, that number moves, but it's not going to be guaranteed to be either 0 or 1. So what can we do? Well, what we can do, and I'm going to disappear for a second again. What we can do is that we take in the vector, okay, so we look through it, and we say, right, so we say for each element in our vector, there you go, for each element in our vector, check whether, in fact I go DP, but for you to understand, fly position or hypothesis, or whatever you like. Fly position is nice, because basically it's a vector of coordinates, at least in our imaginary space filled with imaginary flies, whose positions are the solutions. So for each element, okay, check whether the element is bigger or smaller than 0.5. So for if that is smaller than 0.5, then what do? But then you have to keep track of that. So you would need a sum number, and you add the, am I correct? No, sorry guys. This is fine, okay, I'm gonna check it, but I need a couple of, this is not a double, in fact, I don't need a double there. Int sum int product. Do you remember? We are looking for a sum equal to 36 and a product equals to 360 in group 1 and in group 2. Okay. Now let's start with 0. Let's say initially our groups are empty. Now this fly comes in when we check, okay, and it's a fly in this worm, and we say, okay, so let's have a look at your position. Oh, your position is this array of numbers. Now let's check each position, each coordinate has a certain value. If this value is less than 0.5, then it's in group 1. So we're going to add to the sum, which is our group 1, we're going to add the place of this vector plus 1. Now why? Because our vector, come on, this is silly. Our vector is a vector that has boxes, you know, it's like an array filled with numbers, and the array itself goes between 0 and 1. Our vector goes between 0 and 10. So if we add 1 to the index, okay, it's like if it went from 1 to 10. So for example, let's say this starts card 1, fly position 0. Let's say this is card 1. Card 1 is less than 0.5, so sum plus equals 0 plus 1, 1. Card 2 now comes in. Let's say even this one is less than 0.5, so it's in group 0. So again, this is true. And again, sum, which was 1. Now we added 1 plus 1, 2. So it becomes 3. Now, card 3 comes in, and again, count 3, let's say that in this fly is less than 0.5, so again it's group 1, so again we have to add it to the sum of group 1. And again, this is 3 plus 1, 4, and so forth. So if we take the index of the vector, which goes from 0 to 9, and we add 1, it goes from 1 to 10. And by doing that, we can just add that index, that modified index, to our sum. Oh, progressive, don't need you really. If fly position is, well, in fact, no, else prod, which is our product, times equal, again, we do the same trick. So our index times plus 1. Now, that also makes me realize that we need to change it, because otherwise this will always be 0, because otherwise we always multiply by 0. Now, what this does is that let's go back to our imaginary example. We've had 3 flies coming in, 1, 2, and 3, and they were all group 1. Let's say that now they are flies 4 comes in, and that has an index. Sorry, not flies 4. It's always the same fly, but the fourth dimension, the fourth coordinate of this fly is bigger than 0.5. Then that means that this fly is proposing a solution where card 4 is in group 2. So what we need to do is we need to say, okay, well, now 4, the index 4, has to be multiplied by our group, which is nothing at the moment, is 1, which is obviously the empty group, the product where no card has been multiplied by at the moment. So it becomes 4. Now again, the index of this goes between 0 and 9, so card 4 would be card 3, so we add 1, and that's card 4. Card 5 comes in, and card 5, the coordinate 5 is bigger than 0.5, because this fly is proposing that card 5 is also in group 2. And there we go, we add 1 to the index 4, and it becomes card 5. We multiply card 5 times 4, because now this is 4, because card 4 has gone already. So 4 times 5, 20. And then we continue until the end, until we've checked all of the features, all of the coordinates that this fly is carrying with it, is proposing as a solution. And what do? Well, we need to actually calculate the fitness. We need to estimate, we need to make a measurement of how good this solution is. To do that, we could add some, we could subtract 36 from sum. Okay, so fitness equals sum minus 36. Why? Well, because basically, if we are trying to get a fitness which is as close as possible to 0, 0 is solution found, basically, then the bigger the sum, or conversely, the smaller the sum. In fact, sorry, that's better, right? So the absolute value of sum minus 36, this number is gonna be bigger than 0 every time the sum is not 36, because if it's smaller, then we subtract 36, and it's obviously a negative value, but we do the absolute value, and that's a positive value. Or if it's just bigger, we take away 36 and there is some remainder. Now we obviously need to account for the product as well, because perhaps, we don't know, group 1 is actually 36, but group 2 is not 360. Now, if we think logically about this is not really possible, because providing this algorithm has a solution, this problem has a solution, we shouldn't really have an example where you've got the sum equals 36 and the product not equal. Well, in fact, you might. I haven't thought about this, but yeah, you could. In fact, you can, because you swap the cards in a way that... Right, I'm not gonna actually keep thinking about this because it's gonna slow the tutorial down, but just to avoid problems, I'm pretty sure you might have. If not, it's still, we can't ignore this, because we're not sure, and if we're not sure, then definitely we should, we're using an algorithm. We're creating a program to solve our problem, and that means that we assume we're not able to solve it, or we don't want to solve it by ourselves. So we're not going to try and eyeball the solution. We just want our algorithm to solve it regardless. So what do? Product minus 360. There is one problem with this. Okay, this will work, just that, say we have a card of 5, okay, a value of, not a card, but a value of 5 missing from here and present here. This could be a card, an actual card 5, or it could be 2 cards, 3 and 2, so that the sum is 5 and the product is 5. No, it's not. Okay. No, I'm basically humiliating myself in math. But the bottom line is that what I'm trying to say is that we could easily get a sum, okay, let's say 3 plus, I don't know, whatever, that is equals to, I don't know, 40. So that would give us an error of 4, okay, but perhaps the cards, most likely the cards that make up this other bit here, okay, don't know, 5 plus blah 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 equals maybe 700, okay. Now, if another case is, for example, blah 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 equals 42, but for some reason this one is equals to, this blah 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 here is equals to 500. Now, I'm just throwing out there totally random numbers, but as far as we know, this could happen. I mean, we know nothing about the solutions, and we don't want to, or because we're lazy, or we can't, because we can't think of a solution. We want a program to solve it. So basically what we want to avoid is, we want to avoid this to have a huge impact on the fitness. We want to avoid this solution to look better than this, because yes, this is much smaller, but this is not that much smaller. So perhaps it's just the fact that this is a multiplication and can, this is a multiplication and can get much quicker, much bigger quickly compared to this. So to avoid this, what we do is, okay, you know what, this is 360, this is 36. So if this says an error of 4, and this is has an error of, say, 400, to equalize that, we multiply it by 10. If we do this times 10 and we keep this the same, then we balance them out so that the overall fitness is going to account in equal parts from the error given by the sum minus our target, and our product minus our, and the product of the group, the second group that this flash proposes, minus our target. If this is 360 and this is 36, then we get 0. If this is 36 and this is not 360, then we don't get 0, and vice versa. And if these are different, well, basically the farther away they are from the real solution, the bigger this number would be, and that means that our algorithm behind the scene will know that this solution is farther and farther and farther away. So now we have a fitness function. Let's just test if this works. First of all, does it build? Is this okay? Yes, it does. So what do we need next? Well, where we've got this hello world, we want to run, we want to generate, this is not pointed, we want to generate a swarm. Now if we just generate a swarm, okay, because of the reasons, because of how I set it up, because of how this works, to work with a single range that is mirrored into the negative axis, and actually this is going to start to move flies, not move, but it's going to generate a swarm of flies that has values between -1 and 1. Okay, we've set the search space, but we mirror. Now don't worry, that's not a big problem, because I've got another function set up that your ID should suggest you, which is generates swarm positive axis. If we have a width of 1 per dimension, it will generate a random number for each dimension that goes from 0 to the search space width. In this case, a number between 0 and 1. Brilliant! So now we've got our swarm, and it's by default 20 agents, and each agent is has a dimension vector of 10, so 10 features, which in our case are 10 cards. We check whether this card is bigger or smaller than 0.5, and we move them accordingly. Now, because of how this works, we don't care whether later on the algorithm moves the flies further away than 0.5, further away than 1 and further away than 0 in the other direction compared to 0.5, because this algorithm will still consider any number bigger than 0.5 or equal to 0.5 belonging as indicating that that card, the card that index plus 1, is into group 2, and equally any number smaller than 0.5 belonging to the first group 0. But in terms of generating the swarm, we don't want to skew our random initialization towards group 1, that is group 0, or the first group, so we just make a random number between 0 and 1. So the 0.5 is right in the middle. Then we need to check. Now, check means running the algorithm, and it's as easy as calling this method. Then we want to know our solution, so how do we do that? Well, what we do is that we need to find the best, get best index, and this index we're gonna, well, first of all, DFO, we want the swarm, so this is our swarm. It's a vector, and we want to get the best index, and we put it. This returns an int, by the way, right? Int index, and then we put it here. So what we're doing is that we're saying, okay, right now, our vector, our swarm, first of all, we want to know, after one iteration, what's the index of the best fly. That's the best index. Now get me that fly. That fly is a fly object, obviously. Fly object. Oh, actually, it's a DFO object, isn't it? So, 1 sec. No member F in fly. Brilliant. Yeah. Oh, that's a pointer. Okay, right. So that's fine. We create a reference to this thing, to our fly. Is that correct? Oh, it's a share pointer. Right, ignore all this. You'll have to, I was trying to basically spread it open for you, but you'll just have to trust me on this. What do you do? We want to print out we want to print to console the solution vector of the best in the swarm. And how we do that? Well, there is a method to string. Brilliant. Okay. Now we're going to get basically a stringified version of this vector, and we also want to know, well, we want to know which fly this is. So let's say that we are going to find out what this is. There we go. So fly number, and we get the, oh, so it should be here, fly number, best index, and then we get solution and the vector of this of the fly. Now this is not necessarily the solution, because as we can see here, if we print the fitness, that this may not be 0. Why? Well, because we've only got one run, okay? So unless our flies, our initial flies happen to fall upon a get fitness, yes, happen to fall upon the right solution, and then the best in the swarm will be the right solution, then the fitness of that would not be the best and will not be 0, and that means the solution is not correct, but we're gonna get an indication of how far away we are based on the fitness, if I've set this up correctly, which we're gonna find out soon. I'm also going to do this because I want to leave an empty space, and let's run it. Brilliant. So fly number 18 has a fitness of 180 and has these various values, okay? Now what does mean? What does that mean? It means that card 1 is in group 1, bigger than 0.5. Card 2 is smaller than 0.5. That would be group 2, and so forth. Now if you really want to be alright, you know what, I really want to know what this is, well, then we should probably do a bit of arithmetics to it, but because this is a string, it's just gonna be a little pain in C++. Well, it's easy, but that's just gonna get us away from what we're trying to do here. So let's just say that we keep this as a fine representation of our solution. Every time we see a number which is bigger than 0.5, this is smaller, this is bigger, this is smaller, okay? That means that it's either in group 1 or 2, or 0 and 1, that is first group, second group. And as it goes, if we wanted to write this down, it would be card 1 in group 2, so we've got nothing, and then, okay, so sum and product. Okay, so group 1, group 2. Group 1, we've got card number, sorry, in group 2, we've got card number 1, we've got card number 3, see, this one here, card number 1, 2, 3, 4, 5, 6, 7. So we've got 7 and we've got 10 times 7 times 10. Now, obviously, we can quickly work out that this is 21,210, smaller than 360. Okay, the sum would obviously be wrong, and we could quickly work out why this is wrong and how far we are. How do we take advantage of DFO? We take advantage of DFO by running it multiple times. So say we want to give ourselves 50 attempts, and in these 50 attempts we want our algorithm to try and find our best solution. So now we're going to get the number 50 here, and plus plus I, and then there we go. So we've got DFO update swarm 50 times. Also, we want to keep track of what's happening. So let's say that by doing this, what are we saying is that if nothing, we're saying that we generate this swarm, okay, a swarm that has a dimension swarm that is searching through a space of 10 dimensions. A space of 10 dimensions means that each fly in this swarm carries a vector, a solution vector, a position vector, however you want to call it, of 10 values. These values will be tested against 0.5. Initially they will take a value between 0 and 1, and it's a random value, and then each of these will be tested against 0.5. If it's smaller, we say it's in group 1, and we add that value, the value of the card, which is the index plus 1. If it's in group 2, if it's bigger than or equals to 0.5, it's in group 2, and we multiply it. Now we run the update function of the algorithm 50 times, and each time we check which one is the best fly, what's the solution that it offers, and what is the fitness. Now I warn you, sometimes this can get pretty wild, okay? These numbers might go berserker, really far off. That doesn't mean anything, because we're testing against 0.5. So what's happening is that the flies might be chasing a solution by flying away from what they are finding initially, and that flying away might push them further and further and further, because maybe this one is getting bigger and bigger and bigger, but this is conversely getting smaller and smaller, and by doing that, even negative say, by doing that, they're actually getting closer to the solution vector. If we wanted to avoid that, we could force the flies to only update within, now update is the same, we could force the flies DFO set constraint. Okay, if I did this, this will always be within 0 and 1. Because it's not really needed, I'm going to avoid that and see what happens. Okay, let's see if I find the solution. Let's run this. 20 flies, 50 times. Oh, there we go. Fly number 0, fitness 44. What did we start with? 54. We started with 160, 100, 100. Then we go down 58, 54, 54. That's pretty good. Let's run it again. Started at 34, got stuck at 24, and we run it several times, so we're getting a bit stuck. when this happens, you can try to do something that I think I mentioned earlier, but then I ended up not doing it because I just wanted to quickly get started and not and learn from experience rather than just tell you, oh, we're gonna do this because I know it works. Now let's try. So basically, we're gonna set the democracy to true. We're gonna do it before we generate this worm. It shouldn't matter, but it's just best practice. Let's say that this bit is when we've got all set up and we want to actually generate and then update. Here we set up. Okay. Now democracy means that instead of keeping track of the best in this worm, we are going to only have a look at what our neighbors are doing. If we run this, oh, fitness 10. What did we start with? 130, 40, 34, 34, 24, 24, 20, 20. Well, nice, 10. That's good. Let's try again. 30. Ah, gotta be stuck there. 30 again. Starting from 80. Getting a bit stuck again. 24. Right, so we're not really getting to 0. But we are decreasing. So at this point, there are only two things that we can do. We can either allow our flies to try more, or we increase the number of flies. Now, if we choose to run the algorithm for longer, that's fine. If we decide to increase the number of flies, that's also fine. Ideally, we would want to keep this increases as small as possible, because the whole purpose of this is not to try all the possible solutions at random. So, set population. In my case, I want to say, you know, or instead of having 20 flies, let's start with 80 flies. And we test them. Now, if we were to get to 0, I want to know how many iterations it took me to get there. So, here are iterations, and this is just gonna be I, okay, plus 1, because first iteration is 0 and so forth. Out to solution. Yeah, we got there. Oh, sorry, that me being very silly. What I wanted to do is to check. But by the way, just before I go on, fitness 0, we did get there. Okay, and we got there pretty quickly. We started from 20, and after a while, there we go, 0. It was the same fly, I think. No, it wasn't. Anyway, we got there. What I want to say is that if the fitness is equal to 0, then break. Don't just break, also tell me how many iterations it took me to get there. And I make this, okay. And now this is unreachable in case I break, so make this. So I do the same, everything is the same. I'm just basically saying if I do get to 0, there's no point in checking any longer. Just tell me how how many iterations took me. Try again. 7. Try again. Well, 1, just got lucky. 8. Seems pretty good. Now, what I want to finally conclude this with is to show you how many checks we've done. Okay, so we are going to do this. Checks, and our checks are the iteration plus 1, okay, our cycle, times 80. And let's have a look. How many times do we check? 320, 560, in this case, we didn't get to the solution. We got stuck at 10. You see, this happens as well. With this type of algorithms, we are not necessarily sure that within a set closed number, fixed number of attempts, we will ever get to the true solution, to the optimal solution. What we know is that we're gonna get a really good solution, if not the best, pretty quickly. And again, we didn't get there. And we did get there, yes, first attempt, 240. Now, what I'm trying to say with this is much smaller than 1024. We've got an algorithm which is working, and in case you wanted to go through the code, you will find a better version of the algorithm. By better I mean slightly more organized in here. So I'm just going to get rid of what we've just built together, and there we go. This is what you find inside of the project. It has the very same structure, just that I use a class to wrap up what we've seen together. Populations, democracy, it's all the same, very, very same. This is the checks, and main is basically just calling setup, calling run after setting up the game, and inside, this is just a header, inside our class, we've got the very, very, very same things we built together with some useful comments. And if we run it, there we go. We are getting our solutions, aren't we? Oh yes. Again, stuck at 20. Seems like 20. The fact that we are always getting stuck at 20, now this we got there in 27 steps. The fact that we always get stuck at 10, 20 means that the combinations of cards that create those two numbers, and I think it was 34, are local minima, and that means that they are good solutions surrounded by bad solutions with a slope that kind of suck the flies in if they happen to get there, so that they think that there is not really something better than that fitness is the lowest they can ever hope to get to. The algorithm has an inbuilt method to send sort of scout flies away according to a certain random probability, but in this particular example, if you were to rely on that, well, because it's random, you can't be guaranteed that that would get you out in the amount of iterations that makes this algorithm better than just checking 1024 possibilities. But in bigger systems, in bigger environments where it's not just it's just 1024 possibilities that you can by hand check, but it's just maybe millions or thousands and thousands. Well, this algorithm gets you to a good working solution pretty well, pretty quickly. That's all it can guarantee you, although it really doesn't really guarantee you anything, but in practice it will show you that it works that way. But the con is that it's not a procedural, arithmetically stable, sorry, not stable, arithmetically proven method that will give you the best solution within a certain number of iterations. It doesn't guarantee you that, it will not give you that, but in a few steps what can give you is an optimizer that can search for good solutions and most likely finding the best solution quickly or within a reasonable amount of time and computational power. This is it. The folder that I'm giving you with the repo contains another example in Open Frameworks, and I might add more later. But to use this you need Open Frameworks, so there is an explanation on the README on how you can do that, but this is basically just outside of the scope of this tutorial. So to recap, what we've done in this tutorial is to quickly show you how you can set up a DFO optimizer within your own project to solve, in this case, a simple card game, or to give you a pretty good solution in a reasonable amount of time, using, probably saving, computational power compared to just trying random solutions. And we do this in 3 steps. Let's say we create a DFO algorithm. Where is that? I need the we create a DFO object, and either use a pointer or an actual object, doesn't really make any difference. We set the fitness function and the variables that we need to set so that this swarm will search within our search space, within the boundaries of our problem, rather than any default value that I might have given it. And then third, we generate the swarm and update it, checking all the time where are we in terms of fitness, checking where the best in the swarm is, in fact, in terms of fitness, and returning what we get. So step 1, set up the DFO object. Step 2, send in a custom fitness function and variables to suit our problems. Step 3, run the algorithm. You always need to generate the swarm in step 2, because otherwise this will give you an error. And you can choose whether you want to generate the swarm in the positive, hyperoctant, that is positive sort of quadrant in 9-dimensional space, or you want to generate random positions. This would work, okay? The reason I'm not doing it is because I don't want to start with random numbers that are sort of skewed towards the first group. But as you can see, it works, okay? Because it doesn't matter if these are big, small, negative numbers. We've created a fitness function that can handle that. I've also shown you how to constrain if you wanted to by calling the set constraint to equals to true, but we've also seen that it doesn't really add to our algorithm, and in fact for some reason it creates a hindrance to our path to the best solution, so we don't use it. And this is it from Francesco. Hope you enjoyed the video. I'll probably be back soon explaining some more artificial intelligence and showing you how you can apply algorithms such as this one into your own projects, and showing you how to set them up correctly for your own projects. So yeah, hope you enjoyed it. See you later. Bye.